Okay, so continuing along with this mirage situation, you're standing over here and you're seeing, what are you seeing? Okay, remember we said that it's hot on the road, the air is hot beside the road. Hot air means a lower index of refraction. As you go further up from the road, the index of refraction lowers. So in this case, we have light maybe coming from an angle, let's say over here. And normally the light would want to travel in a straight line. If the light hit a sharp interface between two media, the light would bend at that interface. But we don't have a sharp interface here. We have a gradual, well, maybe not too gradual, maybe it's somewhat abrupt change in the properties of the medium, going from a higher to a lower index of refraction. And what that means is when you go from a high to a low index of refraction, the light is going to bend away from the normal. Okay, so you can imagine we have this hot air down here and cooler air up here. There's kind of a fuzzy boundary between the hot and the cold air. It's not a sharp boundary, so we don't get a sharp bending of the light. But what you get instead is a gradual bending of the light, and it bends away from the normal. So the normal would be, if this was our approximate interface between the hot and cold air, it's horizontal. Normal is this direction, right, perpendicular to that interface. Bending away from the normal means the light is going to bend in this direction, okay? And if the angle of incidence is great enough, so the light is coming from a place, the light is, the angle of incidence between the light coming in from the source or point C and the normal, it's a big angle, right? If it exceeds the critical angle, then what you're going to get is reflection. So this is kind of an illustration of total internal reflection. It won't be the case that if the light is coming from up here and coming down through the cool air and hitting the hot air, it will bend, but it won't be able to undergo this kind of effective reflection that you're seeing here. I know it doesn't look like reflection because it's a smooth bending of the light. Again, that's just because we don't have a sharp interface between the cool air and the hot air. But this is what you're going to see if the angle of incidence is great enough, okay? And let's see, what does it look like to the observer over here? Well, the observer is seeing light which is tracking this trajectory, but what will appear to be the case to the person looking is that the light is coming from, your eyes, your brains just automatically interpret light as traveling in a straight line. So it will look like the light is traveling along this trajectory, right? You can't tell that the light is actually traveling along this curved trajectory. It will look like the light is traveling from over here. It will look like there's some kind of source of light, maybe at point D over here, which is causing the light to go directly from D to your eye. That is an illusion. It's not real. The trajectory of the light, of course, travels along this path, but it appears to the observer like it's traveling directly from point D to their eyes, okay? So how do you interpret that? Well, when you see light coming from the ground, well, why would you see light coming from the ground? Well, maybe there's some water here, water on the ground, and light is simply reflecting off that water, and you're seeing the reflected light off the water. That's what a mirage looks like. It looks like there's water on the ground over here. It looks like that water is reflecting skylight or something, light from the sky, and it's traveling along a straight path from D to the observer's eyes, right? So that's why you see, if you look not too close, but if you look at an angle which, along a direction which is almost parallel, but not quite parallel to the ground, you will see far off in a distance, apparently, water on the ground. But there is no water there, right? It looks like light is reflecting off the water. It's not really doing that. What's really happening, as I say for the 10th time, light is traveling along this path here. And why is it traveling along this bent path? Well, it's because of total internal reflection. Okay, that was a lot, but hopefully that makes sense. You might need to listen to that a couple times. I wasn't quite as concise as I should have been, but that's how it goes. Okay, one last thing to discuss, okay? And this is the phenomena of dispersion. So let's see. So electromagnetic waves, well, electromagnetic waves are fundamentally all the same thing, right? They're oscillating electric and magnetic fields. What distinguishes one wave from another, well, there are several properties, but one of them is the frequency, or equivalently, the wavelengths. Okay, when I say equivalently, I mean in that for any given frequency, there is a corresponding wavelength for the electromagnetic wave. And what this figure is illustrating here is the electromagnetic spectrum. And it's way over here, you have very high frequencies and very short wavelengths. Okay, so we have X-rays way over here, right? 10 to the 18 hertz, 3 times 10 to the minus 10 meters. That's a very short wavelength. When the wavelength increases a little bit, when you get to around 10 to the minus 8 meters, or equivalently around 10 to the 16 hertz for the frequency, you're in the ultraviolet region. And there's a range of frequencies and wavelengths that define what the range is for ultraviolet electromagnetic radiation, likewise for X-rays. There are also, you may know this, past the X-rays, there are gamma rays, which for some reason are not included in this figure. Even higher frequencies and even smaller wavelengths. So ultraviolet is here, and then we have this narrow band of what we call visible light. And as you go from the shorter wavelength, so you're in the violet and then blue and then green and yellow and then eventually red, the visible region of the electromagnetic spectrum goes from about 400 nanometers for violet, bluish violet light, to 700 nanometers to red. Beyond that, you get into beyond red, infrared. You can't see that anymore. So that's lower frequency, even higher wavelength. And you get to microwaves, so even lower frequency and bigger wavelength. And then you get into radio waves, FM radio, AM radio, and so on. Okay, so what am I trying to emphasize here? Well, each different wavelength corresponds to, well, at least if I'm talking about the visible region of the spectrum, each wavelength will correspond to a unique color. Okay, so 400 nanometers for violet light, and then 700 nanometers for red light, and then you have the other colors in between. Okay, so just think different colors have different wavelengths of electromagnetic waves. Okay, so what is dispersion all about? Now, it turns out that what I told you before was not completely correct. There's not a single number, which is the index of refraction, for any given medium. The index of refraction is going to depend very slightly on the actual wavelength of the light. Okay? So what this is going to lead to is a dispersion of colors when the light is refracted. So a dispersion of colors, what does that mean? Well, imagine that we have so-called white light hitting this face or side of a glass prism, a triangular glass prism, just a triangular piece of glass. Okay? White light is a mixture of all the colors. Okay, so when you hear the expression white light, it means not just one color, but a mixture of all the colors. So you have wavelengths of many different wavelengths kind of superimposed on one another. Now what happens is when it hits this interface, the light will bend, and the light will bend towards the normal. So here's the normal. This dashed line is normal to this surface. It will bend towards this dashed line, but how much it bends will depend on the wavelength. So remember, white light is a mixture of different wavelengths, different colors. The red will tend to bend a little bit less, and the violet light will tend to bend a little bit more. And then if we continue along to this second interface, same thing. We expect now going from glass to air, the light will bend away from the normal. Well, red will bend a little bit less, violet will bend a little bit more. So what you end up getting is a dispersion of the colors. We have a mixture of colors here in white light, but the colors will break up into different colors as they emerge from this side of the triangular prism. Okay, so let's do a little calculation here. So we have a glass prism, we have white light striking the prism here. It goes straight into the, because it's incident, has normal incidence perpendicular to this surface here. It just goes straight through without being altered. Well, the wavelengths may get altered and so on, but not the direction. And then it hits this angle here, and then what happens? Okay, let's say that this corner of this prism, so this is a right angle here. Let's say this is 40 degrees. If this is 40 degrees, alpha, then the angle of incidence, you can do some geometry and argue that this is alpha as well. So this is also 40 degrees. So let's see, what is the angle between the rays of light for lambda equals 700 and lambda equals 400 nanometers? Okay, so what do we need to know? We're going to use Snell's law. We need the indices of refraction, and the index of refraction for air is approximately 1, regardless of wavelength. Now, for glass, we're going to use the fact that the indices of refraction are slightly different. Now, I'm noticing here I used 800 nanometers. It should be 700 nanometers. So this is, so you please correct this in the notes. This should be 700. This label should be 700. I don't know why I put 800 here. It's 700. Okay, so N400 just means the index of refraction for a wavelength of 400 nanometers. And this should be lambda equals 700 nanometers. Index of refraction for 700 nanometers is close to, but slightly less than what it is for 400 nanometers. Okay, so let's use the using Snell's law for the 400 nanometer light. Here it is. So N400 is its index of refraction inside the glass. The angle of incidence is alpha is 40 degrees. The index of refraction for the light, regardless of the wavelength, in air is 1. That's why I have a 1 here. And the angle is theta 400. So our one unknown is after we substitute in this value for the index of refraction for the 400 nanometer light, 1.538. We find the angle of refraction is 83.34 degrees. So that means the angle between normal and this ray corresponding to the 400 nanometer light in the air, this angle is 83.34 degrees. And so let's do the same thing for the 700 nanometer light. Again, this should be 700, and this should be 700, and this should be 700. And here's another typo over here, this 400. That should be 700 as well. And this should be 700. Boy, a lot of typos here. When we solve the same equation, Snell's law for this, we get 77.02 degrees. The difference, the angle between these two rays of light will simply be the difference in these two angles, which is 4.32 degrees.